Yeah, so I also put Steven's name on this talk because it is based on stuff that we've done together, and all the demos that you will see are programmed by him. This is not totally original work, I would say. The original work at the basis of this was done by Charles Gunn. Steven was somebody who tried to decipher his thesis by programming it out, and then I tried to write it down in a way that I could understand it, and that this is the reflection of that. So you've seen a little bit about the geometric algebra, you've seen a bit about notably the PGA, which is supposedly a good algebra to describe Euclidean motions in 3D space. But, well, there's more. If you really want to do motions, then you would also like to do motions of heavy objects, not just of these ephemeral lines and planes that are infinitely thin, points that don't weigh anything like that. And we know how to do that. There's Newtonian classical mechanics that used to be described by vectors. Does PGA give another way of talking about that? Well, it does. And this talk will show you how we could get a coordinate-free geometrical representation of the things that we're interested in. That the linear things of sliding and the angular aspects of turning will be unified in a way that works both for the objects and the motions. So we're not going to develop a separate motion representation and a separate object representation and somehow say, oh, if you want to go to motions, you have to go to this weird space of quaternions. No, you can divide two lines and get the motion that turns one line into another. We will show by Steven's software that it's very easy to integrate the resulting equations numerically, but we'll also show that the vector methods are contained in there, and you can very easily, if you're used to doing these things by vectors, embed that, upgrade it, and get all the symmetries and advantages of the PGA. There is some historical provenance in doing it this way, the screw theory and the spatial vectors. I'll relate a little bit to those at the end, but it's more easily developed from scratch just in the PGA context, and then we'll do the correspondence later. It's not that hard, so an hour is enough. Okay. I first want to show you a little demo. And that should be contained here. Oh, sorry, the merchandise. That's always me. So here you see an implementation by Steven of something that we should be able to do at the end of this talk. So I can drag points around. There are springs there. There's clearly a mass that has some heaviness. There is a gravity that tends to pull it down. And when I twist these things around, the motions are made by the Newtonian mechanics that these things obey. And the code that belongs to that is rather compact. There is a little bit to generate the block, which is up here. You have to describe something about the inertia. You have to include the forces. We have gravity, damping. We have the hook spring, both hook springs. This is the equation of motion. This is the integrator, and that is the picture. That's how simple mechanics is. And we do that by encoding that in an efficient way using the primitives of PGA. I'll go back to the full screen. Give many a shock. So what we're going to do, I give first a preview of what will be the outcome so that it gives you a bit of focus. What we'll be able to do is do everything in terms of bivectors, dual bivectors, describing how an object moves, what its body properties are, and there will be something about momentum and forces, of course, because that is what's going to cause the motion. And this will be the full framework that we're going to use for that. So these red letters are the PGA thing. We will be able to make correspondence to how things are done classically, and there's several things to notice. Angular and linear momentum in the blue is the classical way of encoding it with an angular momentum vector and a linear momentum vector. Forces and torques are separate. Somehow they interact when things happen. And there's a few things to observe there. So rotation and translation are apparently in the red side completely unified, classically not. We do recognize all the classical things, but in classical things you have to be very careful where you are when you do it. If you have a force that is acting here and you go and stand here, then there will be an extra torque, and you somehow have to compute it by formulas like this, and you have to remember that you have to compute it because it's not automatic. Whereas in geometric algebra you see that somehow this force that I have here, there's an equal sign here and there's another equal sign here. This is exactly the same algebraic object that describes a force relative to a point R or relative to the origin when it requires a torque. This is going to be a very unusual property of the system that we could call coordinate freeness. It doesn't matter where you are. The object remains exactly the same algebraic object. You choose later, okay, if you want to stand here, you want to know what the force and torque are, you can compute that, but the element remains the same. And that is true for all the aspects. So it's truly geometrical in that sense. And the trick to do that is to go to bivectors and dual bivectors. We are going to have to make a distinction between those two. So the agenda of the talk is I'll talk a little bit about the geometric primitives, so the how to make elements of geometry. Much of that you've already seen, but we'll just do it again, but faster. Then I want to describe about how to characterize motions by bivectors, because that's going to be central. This differential equation that we're going to set up is at the bivector level. We'll then talk about Newtonian motions, so how to give objects mass and what the consequences of that are. And at the very end, I will show how you can take your classical system, make it into PGA, and have all the advantages of this unified approach. Geometric primitives. We have seen this several times already, that we're going to work in 3D PGA. That's the plane-based geometric algebra. We know that for 3D that is four-dimensional because the basic vectors act as the reflection operators, and you can do 4 reflections before you get saturated and in 3-dimensional space in planes. And then when we represent a plane in that space, we use a normal vector and we use a distance to some kind of an origin, which is very, very similar to how you do it in homogeneous coordinates, where you also put a normal vector. You have to make a 4x1 vector with the normal vector here and minus d over there to describe the linear equation. And the special thing about PGA was that there was this one weird vector that squares to 0 to make it Euclidean geometry. When you do that, you get something that is actually for sale. It is the coffee table, or the table on a coffee mug, of all the elements that are in the PGA. So this is a 3-dimensional geometric algebra. The planes are the vectors. If we meet 2 planes, we get the lines, so they're of grade 2. If we meet 3 planes, we get a point, so they're over here. If we look at the planes used as a reflector, we are here, and the point reflectors are over there. If we use the lines to do our motions, then if it's a finite line, we get a rotation operator. If it's a line at infinity, we get a translation operator. And if we combine all those, we get the motors, which are, they've been called rotors in general, or versors. We'll call them motors when we talk about this algebra. And you see that lines are represented by 6 coordinates, very much like the Plücker coordinates. We will see that they'll form screws to describe motions, which is very much like a Lie algebra of the motion. This is the regular homogeneous coordinates at the point-based level. This is how you do normal equations. And we'll also see that the quaternions and the dual quaternions are in there. And the nice thing about this is that you see both objects and operators unified in a single framework. Nothing is unused, and the relationships between the things are not just table relationships, but actually algebraic relationships. If you multiply 2 planes, then you get a rotator. We have seen several examples of that, and I'll demonstrate it as well. So this looks like a very nice system. What you don't see in here yet in this picture is where are the forces, where are the momenta, etc. So we're going to have to extend this a little bit from this simple object picture to a dynamics picture. So we'll probably have to make another mug when we're done. The main focus of this talk will be on this part, because this is where the motions are. not the reflections, because that's not Newtonian mechanics, but just the continuous motions. So just to rehash a little bit, if we have two planes, we also have an operator that makes the intersection between the two planes. That was the wedge, and that produces a line now on the coordinate basis of, well, the composition of two vectors, so all the possibilities that you can make in the PGA to do that. If you do three planes, and maybe this is a good example to do in a little bit more detail. So how do I make a point at a certain location from the origin? Well, I take a plane maybe, perpendicular to the x-axis at a certain distance, perpendicular to the y-axis, perpendicular to the z-axis. I do the wedge, so that meets all these things. And if I do this, here you see this first plane in E1 direction with x1, E2 direction with x2. You just use the wedge product to compute this, and things naturally group into something that you can then briefly write as E1, E2, E3, that's the point at the origin, that's where the three origin planes cut, plus x times something at infinity. Okay? Doesn't matter. There is apparently something with a coordinate 1 and something with the coordinate x1, x2, x3 that I need, and that is precisely what we would recognize as homogeneous coordinates, except that the basis on which this is now expressed is the 1 goes with the E1, 2, 3, and if you see where the x1 goes and you look that up in this equation, you see it's 0, 3, 2, 1, etc. These are actually the points at the coordinate directions at infinity, and by making a combination of these things, I can get a representation of a point. So you see that these pictures we've seen from Stephen and from Martin of the three intersecting planes forming a point because it's a point reflector, etc. This is the computation that goes with it. It's extremely simple. It's just using the properties of the wedge product. There's something very unusual going on in this representation. It's actually also true for homogeneous coordinates, but I'd never really realized it. So let's say that I've been at the origin and I move over a distance p to a point that I'm interested in. So I would represent this as the object O plus pi. We've just derived that. Now, this is one algebraic object. It's a trivector. I can add something to here, which I then have to subtract something from here so I don't change that object. And now it suddenly takes this form. R plus p prime, it's p minus r, here it is, times I. So it's almost as if my origin is now this, and the point that I am looking at relative to the origin is that. But of course I could have done that for any point. So there's a very strange freedom in this thing. It's very specific about where the point is. I have given it coordinates relative to the point that I originally constructed it. But once I've made this object P, it doesn't care anymore where I want. If I want to stand here, it remains itself. And if I then inquire, yeah, but what are your coordinates? Then I have a look at the factor of I, and then it says, well, the factor of I is this because you're now standing at R. This is totally automatic. You never have to worry about this. You make the object once. It doesn't care in which coordinate system you made it. No, translationally invariant. That's really very handy. If we want to describe things in their absolute relationship not relative to a place where I used to stand and just the time, then this is exactly what we want. So there's a very strange paradox here that you can give it coordinates and you make something that is coordinate free, which you can use from anywhere. You can always ask the question, okay, now that I stand here, where would I see it? But you don't have to change the object for that. So if you set up your equation in terms of these things, they will be totally coordinate free equations. We have another way of making lines. So there was one way of saying I make it the meet of two planes. If I do that, then I usually have plane 1 and plane 2, and I would say that there's an angle between them. So this is clearly sort of like an axis, something that I can rotate around. When I have a point that starts moving, I am more interested in it was here, it goes there, and I move in this direction. What is the line of movement? This has been called a spear. It doesn't have that rotational aspect of it, it has the along aspect. So one of them is around and the other one is along. Both are sensible ways of talking about lines, but if you just look at the coordinates, you cannot distinguish them. They look like the same sort of thing. For us, it's going to be important to make a distinction between them, to make a dimensionally independent, ignorant, agnostic way of characterizing dynamics. So axis is something we turn around, a sphere is something we move along. And these will be the things that will model momenta and forces, but then we're 20 minutes further down. Representing Euclidean motions, it's the only picture I could find of a screw around the time that screw theory was invented, so I thought I'd steal it. It's now going by itself, which is not what I wanted. That probably killed it. The basic organizing principle, we've seen it several times, is Cartan-Dieudonné. You know, we see motions as multiple reflections. We're not going to do them as multiple reflections, but we're going to represent them as if they were. And one of the central things there is the sandwiching, which is that if you want to reflect an element x in a plane A, then you have to do something like A times x times A, except that if A is not normalized, you better normalize this whole thing so the norm of A doesn't occur. That means you should better use A inverse. And if you look at properly what you want, if a mirror reflects in itself, then maybe you want that if this was the reflecting side, then the reflected mirror should have the reflective side here. So let's maintain these signs properly by putting a minus sign in it. But as soon as we start doing two of these mirrors, so I have one here, and I reflect the result of that in the other one, you see that the minus signs disappear anyway. As long as we're talking about these even motions, these motions that I can perform continuously, the rotations and the translations, and forget about the reflections, this doesn't really matter anymore. So this is the way that we perform the mirroring algebraically that Stephen drew in his pictures, and Martin as well. And why does this work? Nobody showed this, and I think it may give you a little bit of a handle on the connection to linear algebra. So in linear algebra, you would say if I want to reflect x in something with a normal vector A, then I would have to take twice the projection and subtract that from my vector. Now in geometric algebra, we say, yeah, but the dot product is just the symmetric part of a geometric product. So I take xa plus ax divided by 2, and then I have the symmetric part. And if I now allow myself, you know, multiplying these things out, have an obvious thing that a squared divided by the norm of a squared, that should be 1. Okay, so that means that a squared should multiply to a scalar. Then I get to this equation. So there's a correspondence between the old way of doing it and the new way of doing it if I introduce a new product, and this, wanting this to be true, dictates the properties of that product. So now we get sandwiching. Like I said, there are some minus signs, but we're not going to bother about those because we only do even transformations. And the nice thing about the sandwiching now is that it's equivariant. So whatever you put in the sandwich behaves correctly. What do we mean? If I had made a line as the join of 2 points, then I could have moved point 1, point 2 and made a new join, or geometric algebra allows you to actually transport the whole line. The result is always the same. And why is it the same? Well, because you can always put these m's in there. So for a geometric product, it's at least so that this property holds. And now as long as we make objects only as linear combinations of geometric products, we will always satisfy that for everything. And that's what we're going to do because the weights product, the dot products, and all these other ones are like that. So this means that you no longer need a method for every data structure. You don't need to specify how a line transforms. Martin was talking about that. The lines, the points, and the as matrices acting on the vectors that represent lines, points, and planes are all slightly different. In geometric algebra, it's all the same, and a motor does it. And these equations haven't been really shown, but I just wanted to show that indeed the wedge product is a linear combination of geometric products. It's the anti-symmetric part, and the other one is the symmetric part. Now, we've seen many pictures of making two planes to make a translation, and we've seen something about a gauge transformation. Let's just do it. So let's take two planes with a normal vector n, but one at the location d1 from the origin and the other from the location d2 from the origin. Is the origin necessary? No, by the same argument I just showed. These are just objects that are independent of that origin, surprisingly. If I just do the multiplication, then n times n, I've normalized the normal vector, is 1. And here I get some others, and E0 times E0 is 0, so that doesn't appear. And now we see just the gauge appearing. Right? The only thing that is necessary to specify this translation operation, even though I started with two specific planes, is that the only thing occurs is the distance between the planes and the direction that the planes had. So I can characterize this by a translation vector. And it doesn't matter anymore which planes they are. We saw animated constructions of why that would be when you divide 2 points to each other. That might have suggested that you have to do something for it to make this true, but it isn't. It automatically happens. It automatically is so that these pieces are put together, and therefore delta 2 minus delta 1 is the only thing that matters, so it doesn't matter if both of them get 100 times further away. It just cancels. And the same thing we see with the rotations. There is, if I take two general planes and I do the product of one plane with the other plane, so I reflect in one and then I reflect in the other. If I put this in the sandwiching product, then there's a bit of hocus pocus in which I should recognize that I'm actually talking about the common line at a certain location, but it is indeed that line. The hocus pocus you can figure out in one of the tutorials. Again, you see that the only thing that apparently happens is the line between the angle between the lines is relevant. And the angle between the planes is relevant, and the line that they have in common. And so again, all these specific things like I used N1 and N2, but you use these two, doesn't matter as long as they have the same angle and the same line in common. So again, this completely cancels out automatically, and you can call it a gauge transformation, but yeah, it's just as easy as subtracting two things and knowing that therefore their absolute values doesn't matter. We will write these things in the exponential form. Joan mentioned that briefly. I understand that you have had Taylor series and exponentials. If you write this out and you just remember that every time you get L squared, you can replace it by -1, then you will find that there's a lot of things that only are scalars and they become 1 minus phi over 2, phi squared over 2, plus 5 to the 4th over 4, over 6, 4 factorial. And those group into the cosine and the rest groups into the sine. So this is equivalent to that. And yes, looks a bit like complex numbers, looks a bit like quaternions. If they're in the origin, if this line runs through the origin, this is a unit quaternion. And otherwise, it is a special case of a unit dual quaternion. Now, so this is nice because what we, for instance, could say that if we want to generate a motion that rotates around an axis, then apparently all I need is the axis itself and the angle that I want to rotate over. And I make this operator, use it in sandwiching, and I can turn anything, because we've also seen that it works on any kind of an object. So there's a direct correspondence between specifying motions by their geometry. Maybe we want to revert that as well. So maybe we want to take a motion and then identify its axis. That's what Martin discussed. That is the exponential versus logarithm and finding how it actually moves. A little bit of a strange thing that we have to get used to is that, and I've drawn it in gray here, that an axis is something you turn around. So you use it finitely to make a rotation like this. If your axis is a line at infinity and you turn around that, then no, if that would turn like that, I would feel myself moving up, right? So this is how I describe a translation. It's also an axis, but it's an axis at infinity. As long as we agree that that is allowed in our terminology, the algebra suggests that. But then when we want to make a general Euclidean motion, it becomes a bit subtle, and Martin has shown that you are not just allowed to add the parts of the two components. One of the things you can do that shows that it's ugly, that if you take a rotation first and then a translation, which is the common way you characterize motions in homogeneous coordinates, you get something that looks rather draconic. There is a grade 0 part, a grade 2 part, and a grade 4 part. Yes, but you can still write that in the form of the exponential of a bivector. If you want to know which bivector, use the algorithm that Martin presented. But this can still be written in the form of this. And if you then want to understand what this bivector looks like, you can still look at Martin's stuff, and you find that you can always write that as a combination of two things. There is an axis that is being turned around, and at the same time there is an infinite axis that is perpendicular to that, which gives the translation. So you get together, you get this screw motion. Is this a good representation of motions to do interpolation and so on? Well, that depends a little bit on your application, but it's certainly an algebraically unique way of describing what this motor M looks like, so that I can characterize it with 6 numbers, the 6 coordinates of the bivector. If you want to compute with that, you maybe think that you have to do very complicated things, but Martin and Steven in their paper Normalization, Square Roots, Exponential and Logarithmic Maps give extremely compact code to take the logarithm of a rotor and to take the exponential of a bivector with very, very few multiplications. So this can be implemented really quickly. I've said that one of the advantages of the PGA is that there is an interrelationship between the motions and the objects, which other motion frameworks do not have. You go to a completely different space to represent your motions, or so it seems. But the ratio of 2 planes is a rotation. The ratio of 2 points is a translation. The ratio of 2 lines is the screw that turns this line and moves it at the same time, perpendicular between the two. And these are simple constructions, that's why the square root comes in, that tie the objects that you want to use to define motions to the actual motion operators, which then are capable of not only moving those objects, but any object, because sandwiching is equivariant. And so that's a really very nice consistent framework. Maybe we should try to use that for physical motions as well as motions in graphics and robotics, where homogeneous coordinates are used. Now there are different ways of talking about motions now. We have homogeneous coordinate matrices. We can use quaternions for rotations and then translation vectors. We can use unidual quaternions, which are more like the motors, or maybe we want to characterize them as these screw bivectors, which are only 6 components, whereas the motors are 8. Steven and I are supervising a UVA student who is going to use these different representations to learn motions from observations. And we are currently finding out which of these representations are most suitable for neural networks to actually learn the motions. And there are some subtleties here. If you just use the screw axis representation, which seems algebraically very nice, uniquely defined, even physicists agree among each other which bivector decomposition works, then it still makes a difference whether you do that in a global coordinate system, which is the yellow axis. So the yellow axes are for each of these little motion steps that I do here. And at one moment I rotate around this axis now, and the next moment around this, because I'm sort of working with a translation, versus the local coordinate system where I travel along and say only the relative motion is this with this axis, and that is indicated in blue. So even when you choose for the bivector representation of motions as the log of motors, there is a choice to be made of how you apply that And this looks much more easily learnable than something like this. A network would really have difficulty with these things that go to infinity. But we're going to find out when she's done in a month or so. A little bit further, because we're actually now talking about motions, and we will of course want to talk about differential motions, because we know that Newton's equations are differential equations. They say the next time step, this is going to happen because of that. If you look at a motion that is encoded like this, so I have an object x0 that is being moved by a motor, then if I want to characterize the bivector of that motor, I can actually derive that from the motor as saying, well, it is the derivative of the motor divided by the motor itself. So it's the relative motion, the relative motor. That turns out to be always a bivector, and that is indeed precisely the instantaneous bivector that you need. If you then say, yeah, so this now means that I have at this moment I have a small axis that I'm turning and twisting around. What now happens to an object x? Then it turns out, and there was also a picture that was on the slide, one of Martin's slides, that such an x moving under the influence of a motor m will get a little derivative that is actually the commutator product of x with this bivector. So the bivector gives complete information about the local instantaneous motion of any kind of a thing. This is not just for a point, this is also for a line, in CGA for spheres. That is how simple it is to take a time derivative of something that is moving under a motor, but you have to know the bivector. And note that there's nothing here that says what kind of a motion it is. This bivector contains both the rotating and the translating motion, so both the linear and the angular velocity rates are in here. I will call this the rate bivector if I do it as a velocity, as a time, certain constant thing per time step. Now, you can either accept this or derive it. The actual general derivation is a bit tricky, because you have to somehow prove that this is always a bivector. But let's look at a very specific case. So let's give a motion with a constant bivector rate. Even there I have to be a little bit careful, because I have my object x0 in my coordinate system, in my graphic system, or where I have defined it. But it starts moving at this location and then starts evolving. So what I just always have is that there's an initial situation that I put it in. This is a rotation translation, therefore it's a motor. And then I start evolving it. So if I say I want to evolve with a constant bivector, it'll look something like this. First do m0 in the sandwich, and then multiply by this. Now, the time derivation of something of this form is very easy. You know that an exponential function is the derivative of its argument times the original function. So this takes this simple form. It was true in calculus, it's still true in geometric calculus. So this is indeed, here we see m dot, here we see bw, the bivector in the world frame, and the motor itself, and that gives that equation that I had on the previous page. Sometimes it might be more handy to say, well, let me first, this thing is evolving, and then I put it at the place, I take it in the origin, I start evolving it in the way I want, and then I put it in where my origin actually was. And this is called the object frame motor. So now I first do my evolution, like a spinning top. This is a very natural thing to do. And then I say, oh yeah, and by the way, the top was over there in this place. If you now do the time derivative, you see that the B is in the other side. So there's a slight difference between world frames and body frames. And when we do the evolution of the Newton equation, it'll turn out to be slightly handier to do that in this frame. But it's an easy switch between the two. How does this commutator now come about? Yeah, well, if I take the time derivative of something that is so composite, I have to take it of the first term. And then I have to leave these alone. This is constant. And then I have to take the time derivative of the inverse. Well, I looked it up in the table. Well, table in my book. So I first wrote the book and then I have to look at the table. I wrote the book so that I could look at the table, but this is in all the books, Chris and Anthony's as well, David Hessener's. This is how the inverse differentiates in time. And then you regroup the things a little bit, and then you see that this m dot m inverse appears here and there on both sides. You're not allowed to move it through there because things don't commute. We recognize that as either this one or this one, and we put them together. We define a new product that says half of AB minus BA is the commutator, and this is now shown for this constant rate that we indeed have this form. Yeah, but you don't need all those details. It does show that the computations are greatly complicated. Okay, so you have to know the derivative of an inverse, but it's not that hard. Let me keep an eye on the time. Let's say? Plenty minutes. Oh, this animation doesn't work now. So we're going to represent a motion by a momentary axis. We're going to expand movement, so a thing that is moving by a local join line. And the correspondence between the two is going to be the inertial mass distribution. And then I wanted to pop up that maybe this doesn't mean much to you, and it just looks saying thing 1 and thing 2 without giving too much details. That's what we're going to do. Cut Benny for the video. And so now we're going to actually Newtonian motion. And I have the feeling that it's automatically walking ahead now. Maybe not. So to go, what we just done is the relationship between if I rotate something, how much does something move? And that you can call that kinematics. And the description between a little change in the parameters of the motion and how much it makes things move. We've done the following steps. We are said planes are reflectors in sandwiching. Even reflectors generate a motor, and we're going to represent that by a bivector, which is like an axis. The bivectors of R301 are compact parameterization of the 3D Euclidean motions, precisely the 6 parameters that we expect to have to say, because there are 3 angles involved and 3 translation things are also number of parameters that are in the bivector. They weren't in the motor. A dual quaternion motor has 8 potentially independent parameters. So also for a neural network, that may not be so good. And to convert that twist bivector rate to actual movement, we use kinematics. What we're going to do now in the second part of the talk is that every movement has a momentum, and that'll be an element from the PGA that is called a dual bivector. We were going to unify forces and torques in something that Stephen calls a fork, because he's funny. And Newton Euler says that a fork changes momentum, and that gives you the differential equation, which you can then integrate numerically. Okay, so here's a big thing in the middle here that we have to work towards. So let's say we have a heavy point. So we have a point with mass m at PGA trivector location x. Let's move that a little bit. What happens? It gets momentum. What happens is that a little bit later it is at xi plus xi dot. But we know what xi dot is. You know, that's xi cross b, if we know that it's moving under a motor with bivector b. And that's the only thing that happens in the joint, so I'm going to stand with the heavy point at this point. I look at a little bit further, and that little bit further is determined by that bivector, because it is doing a momentary motion according to some kind of an axis, which I still have to determine, but that is the relationship between the two. Now, when you look at this expression, this tells you something about, if I do this for all the masses that are in this composite object that I am moving, oh, that's not a rigid body, okay. This composite object that I'm moving, then I have to add all these contributions, and you see something with the x occurs twice there. There's the mass. Depending on how the masses are distributed in space, this will be a different number, but it will be very characteristic for the set of things that I am moving. That's called the inertia. And in this expression, we just say this is a linear function of b. Let's call that linear function I. It depends on the particular mass cluster that I'm trying to move, but I can compute it beforehand. And every time I can say, okay, now this mass cluster has to rotate around this axis and shift a bit. What happens? How hard is that? You compute this momentum to say how much effort, the amount of movement that involves. Seems completely innocent, but you may not trust that this is the same inertia that you may know from classical physics. It is if you do a very stupid split of the bivector into, let's say it rotates around the origin and there is a translational component, and you do the computation of this function, then you will find that there will be a linear momentum involved with, relative to the centroid of this object, that is something like the v of the centroid plus a little bit that it's also rotating because of the b, plus something that you recognize as very close to the classical formula for how you compute inertia and angular momentum. So I want to open it up only later at the end of the talk, but it is in there. This looks completely innocent, but the B contains both the rotational and the translational aspects, and this mass inertia, total inertia that we compute, also still is completely capable of processing how hard it is to translate something and how hard it is to rotate something. It's all in there still. It's just surprisingly simple. So we have that one. What happens algebraically? Well, we put something in that was an axis, and it gives something that is one of those join lines. In 3D, that's very confusing because an axis is a line and a join line is also a line. One of them is an around line and the other one is in a long line. But if you would see this in 2D, your hyperplanes are lines. So an axis is the meet of two lines. So in 2D, an axis is a point. But when things start moving, when points start moving, they move along lines. So then in 2D, you see a clear distinction that one of them is a 2D bivector, which is a point, and the other one is a 2D vector. 2D has a 3D PGA, and 3 minus 2 is 1. So there is a duality relationship between the two. And that is indeed true. This is a duality transformation, and you can easily implement that. And when we look at Stephen's code, that's also what he has done. So it is always so that there's a relationship by the mass distribution between the axis and the motion. Inertia in PGA is additive. Classically, you don't have that. I don't know whether you've done classical computations with inertia matrices, but you have an inertia matrix of this object in this position. You have another inertia matrix of this in this position. You now say, I want these movements to be one object that moves together. Then I have to do an extra computation that says how you have to convert this inertia matrix from the coordinate system of this, or maybe from the coordinate system of the common centroid, to get the total inertia of how hard it is to rotate this total thing. So there is an extra thing where you have to think of what to do, and you shouldn't forget it, because then you get the wrong answer. With this inertia, it is completely additive. So how this composite object reacts to a bivector rate is just the sum of how each of the individual ones do. And that is again related to that same property that I showed you for a point, that you can define things that don't change no matter where you think your viewpoint is going to be. The object remains the same. If you ask the question, you can retrieve what it would be in those coordinates, but just don't ask the question. Don't ask policy. The time derivative of something like an inertia, well, it's a linear map. It moves with the motor. So we will at least expect something. If anything moves with the motor, you get a cross B. But in general, also the B itself may vary. This is a linear function, so the ddt just goes through there. So this is the total derivative of what we expect for the inertia map. And now we're almost there. Oh, we should talk about forces first. So let's say that we have a force. What do you have to say? Well, the force moves along a line. The force acts along a line. So let's take a point on that line, the point Q, and let's take the force vector in Newton, and let's make this join line F dot Q. I was maybe a bit fast in the slide where I derived the join line, but if you have a point Q and you want a line in the F direction, then the geometric algebra object that does this is F dot Q. And this is a dual bivector in our case, because this is a trivector, and a dot product lowers the grade by 1. So it's a bivector, but it's a dual bivector. This has exactly the same sort of properties as I showed for the point. So if we define a force along this line, this blue force, this just exists in space, and it is just represented by an algebraic object. But if I want to know, if I want to move point R and say, what does this object, this force object look like from my perspective, then okay, let's first write it like this. This was O plus Qi. Let's now introduce the Ri, because apparently we're interested in something in location R. Then we have to subtract it here. This organizes completely into something that I recognize the force at R, just like this was the force at Q. But apparently I get an extra term, and I have to do some manipulation to bring it in classical form. But this turns out to be just the torque that I feel at that location. So again, this one fork object remains the same. If you want to know what it is from here, you sometimes may feel a torque. If you displace yourself along the line, you will still only feel the force. Look. But it is all exactly the same object. You don't have to peel it apart to find out what it is. It just is. So that's very handy, because now we can set up the general equation of what is going to happen. A fork, combination of forces and torque, causes a change of momentum. The momentum contains the linear and the angular momentum. This is the equation we need. The P was that thing that we had, which was the I of B. We maybe want to do it in the body coordinates, so that means that the world force is this thing, which was the derivative of that of P in the body frame, and I now have to place it at where I want to be with the forces. You know, I'm doing my computations here, but that means I have to translate, for instance, the gravity force may in my coordinate be rather skew, so I have to transform that back. This is all done to make it slightly easier. We now have to unpeel, because we're interested in the B dot. We want to see how much we have to change the present B that we think it is. And that's just an inversion of this function. And then once we have what B then is, in the next time step, we still have to make the new motor out of that. So there's a coupled set of two differential equations. One says the force via the inertia causes this change in the axis you're turning around. And the other one is, oh, if your axis that you're turning around is this, then your new motor will be that. And this is how it integrates. Let's see a demo. Oh, this is not the one I wanted to show. This is, for instance, one of those things that we can demonstrate. So here we have a block that is hanging from a certain thing with a string. I can run it again. And if you look at the equations, then you see that I have defined a force of gravity. There is a hook force, so that is the attachment point in one location. Here you see how that is done, or I had a slide for that. Let me go to the slide. At least you see it works. Let me go to the slide first. So here's the code in a little bit more detail. So we have a point in real space that I want to attach one of the corners of this cube to. Here you see what happens. This is the corner of that cube. It's a point with index some number. In order to make the relative line between those two in which I have to apply the hook force, I should take that attachment point in the real world and use my inverse motor to apply to this, so I transform it from the world system to my local coordinate system. Here you see the momentaneous bivector we use to make some damping, otherwise the thing goes numerically a bit unstable. And the gravity force is done by one of Stephen's handy operations. This is dualization. So we first define the infinite line. The E2 direction is vertical. So I have a plane that lies like this, perpendicular to the floor plane. It meets infinity over there, and then to get an arbitrary vertical line, I just take the dual of that. So that's how he has constructed this. And that just works. And what do we have here? Here we have set up the equations. If you remember that m dot was minus 1/2 m times b in the body coordinates, and the b is something that was the relationship between b minus the dual, times the dual, that is the inertia that is in here, because this is inertia that we have defined. In this example, that's the Hodge dual. This has some very nice properties. Steven has been talking about that you would really like to specify these things in a way that that doesn't demand too much on dimensions, and that you can do that because if you characterize things by their normal vector, then you say my normal is in the direction E1, and I don't care how many other dimensions there are. If you want to know what others is on this plane, then you have to evaluate any point with an arbitrary E2 coordinates, E3 coordinates is also on there, or maybe E4, or maybe E42. The only thing I want to say is it's perpendicular to the E1 direction. So here he has implemented that. There's a nice video of him programming this whole code in real time. It takes 10 minutes, but you gradually see it develop. And the interesting thing now is that I have said here that the dimensionality is 2, and that's the initial thing in which he programs it. Then he makes the dimensionality 3, and automatically it changes the block. You have to look very carefully to see where the dimensionality affects the thing. Well, the number of points to make a cube in that dimensionality is relevant, and he attaches it to the last attachment point. I've always been in favor of calling this the 0th point. Then you will see that in all of this code, also in the specification of the forces and in the equation, the dimension d does not occur. So this is totally dimension independent code, and in order to drive that point home, we can even make it a 4-dimensional thing, and now we get in 4 dimensions we get a sort of poor man's 3-dimensional. You can't drag it in 4 dimensions, okay. No drag queens in 4 dimensions. But this is just the same kind of thing. The code is exactly the same because it has been specified not only in a location-independent way, coordinate-free way, but it's even been specified in a dimension-independent way. And there's no other system that can do that. Okay, we'll go to the summary then. So the path we have walked is that we have said that if we start with hyperplanes and we meet them, we get a line which is like an axis. And if we put a rate around this axis, then we get a motion operator. Then we came in with a force. And we have seen that a force is a different type of line. It's a long line. It's a join line. And you could make those by the join of points, just like you made these as the intersection of planes. Now, there was some kind of a relationship between the rate of change and the momentum that caused, and that involves the mass distribution, which is encoded in the inertia. And somehow we have to work our way back up to the b dot and the m to get out of this, which also involves the inverse inertia. But this is the relationships between these things. So the algebraic elements of the dual line and the line, the meet line, are the two important things. This is a bivector, this is a dual bivector. This encodes this encodes that, and the whole is related in this manner. Now that's too nice, so let's break it, right? So we're going to back to vector mechanics, because all these coordinate-free things, and we don't understand them. We really only like vectors. So let's forget that we know about homogeneous coordinates. That's something for graphics people, for roboticists, not for true physicists, because we all know that space is three-dimensional, so why would you use something four-dimensional to represent space, right? Okay, you want heavy points, and so you have three coordinates plus you have the mass, but let's ignore that. Let's say mass is something completely different, doesn't belong in the geometry. Okay, so we forget that. So that means that we lose our vector E0, and that means we now have to trade. We don't have that there are rotors that make something rotate, and exactly the same kind of rotor that make it rotate around an axis at infinity, which is translation. So we have to treat linear and angular separately. Then we automatically have caused that, but we like it that way. Now, we're not using bivectors because we don't understand them. We just use vectors, but we notice that some of the vectors react differently than other vectors when I do reflections or motions. So I have to now introduce two kinds of vectors, polar and axial vectors. One of them are for linear momenta, and the other one are for angular momenta, which react differently. And yes, they're both three numbers, and I'll just have to tag it or have to mind my software so that this goes correctly. I know that my force acts in a certain line, but I want to characterize it with a vector, so I can only give you a force vector, and then in the text I say, oh, this was at point Q. No, I can't make f dot Q as an object because I don't have that. So I always have to go back to the text when I want to go to a different place to see where this was evaluated, and then I have to put it in there. So I need all sorts of extraneous techniques to get my inertia right when I go to a different place, because it's not part of my math, because I haven't encoded it in a vector. And then we tell our students that is how nature is, so you have to get used to it. And we do that for a number of years. Actually, they could have changed after screw theory, which has some of the aspects of the things I was just talking about. If you do that, then this framework, which was, as I showed you in the software, was all we needed. We needed to specify some details of the forces. We needed to specify some details of where the masses were. But then this was a completely automatic framework with two lines of integration. That then becomes something in which, indeed, the linear and the angular aspects are completely distributed, in which if I move to a new location, I have to remember that my inertia matrix is now no longer that, but I have to add all sorts of things because I've moved to a different place. And the same with what happened to the angular momentum when the offset of the centroid. I have to remember all these things, I have to teach all these things, I have to make separate sets of equations that integrate the linear and the angular, even though they are combined. And what I could have done is make a very simple construction. Whenever I have, let's say, a force, I say at which point I have defined that force works. And whenever I have a torque, I say, well, but that's really sort of, it works only on the directional aspects of the thing, so I slap an infinity on it. All of these things are just f dot r and e naught wedge, the other vector, the angular vector. These are the polar vectors. And this is just a dual of that, you know, for the rates, because it's just opposite, which is also a bit confusing, right? So now the translation is here, and here the linear motion is here. So there's something strange going on even classically. All right, because now, and what I could have done is lifted it by taking my classical vectors, and I could have done the linear aspects dot the location where it acts, plus e infinity wedge my angular polar vector. I could have made one PGA dual bivector that is completely equivalent and decomposable into this, but that has much nicer algebraic rules for integration. And that lends us back to this thing. Because I have minus 2 minutes left, I will. So this is all not totally new, in the sense that in other frameworks it was also recognized that there is a 6D structure that is rather linear, that you can appeal to encode the dynamics. We have PGA, but there's also something that is much older, screw theory, and there is something that is used quite a bit in robotics and in Muyoko for coupled motions of things under constraints, that has been developed in something called spatial vectors. These are 6-dimensional vectors. Any of the 6D frameworks is already a bigger improvement than over the two polar plus axial 3D frameworks, because it starts integrating these things. There is some hairy math involved, which for us is completely automatically taken care of by the bivector math of PGA. We have this naught, E0 in there that automatically cancels some terms that you don't want to appear if you would do a normal product. The other frameworks have to hard code in special multiplication rules that are different for whether you're a force or whether you're an angular rate. And that is how spatial vectors do it. The advantage of doing it that way, completely into standard matrix and vector operations, and so you can use existing linear algebra packages and the optimization in there to do that. But they're also disjoint from the object. It's a special motion representation that you jump to do something, and then you come out of that and you move your objects. And we've seen that for us, that's also more integrated. So PGA really cleans things up. Objects and motions in a nicely integrated framework. Bivectors are the crucial motion representation. We unify linear and angular. The inertia is additive, which is addictive. They're very simple and efficient code results. You've seen some of that. And it's easy to upgrade to it, so why wouldn't you? More information about these things, we've written some tutorials in the software is on bivector.net, because all the cool vectors are bi. And here's some more exploration. All right,